Thank you. Okay, so this presentation is interlaced with a bit of autobiographical experience on my part. And in many ways, it's probably going to be not much, there's not going to be a lot of new content to veterans, but I do think it is a interesting thing to revisit, even if you've been in the trenches of air handling and exception handling. So I'm not intending this to be an exhaustive history of air handling or exception handling. I'm not going to cover Golang, COBOL, BASIC, or Fortran. I would love to do that, but I think I would end up writing a course. Instead, I'm going to present on some of the patterns I've seen in my career when I've been maintaining and improving long-running systems. And also, I'm going to intentionally skip over how these patterns can be misused by lazy, misinformed engineers. So I just want to avoid this kind of conversation where language X provides this feature, it's good in principle, but most developers ignore it and do this other thing that causes a problem. So the feature is poor because it drives devs to do this thing because they can't be bothered to use it correctly. So that whole line of argument is just orthogonal to what I'll be presenting. Anyways, so I wanted to do this presentation because as we start to onboard with Rust and we take an interest in our best practices, I think we should take a renewed interest into how we do exception handling and all the tooling that goes around exception or error handling in the language. So I kind of wanted to lead off with something a little weird, but and that is, you know, there's a lot of hate for checked exceptions, but I found there are things even worse than checked exceptions, and now we're gonna, here we go, get my slides back. And so I've, anyways, I found, whenever I found that I've been a checked versus unchecked exceptions conversation, the whole concept of exceptions in and of themselves as a method of flow control should and is often brought into question. And you see some excellent variations in different languages on the try and catch model, like in Rust and Scala, as actually a return type. In my opinion, I think that's a better alternative than the checked exception model. But anyways, that's just opinion. I wanted to get at was one of the problems that checked exceptions were trying to solve, and that is they were trying to get at having intentionality about defining what could go wrong as part of a contract to a method or a function. And as you go through different languages, you start to find that, like, you find out why they made that decision and what problem they were trying to solve. Not to say the solution was good, but it gets pretty awful. So looking at this code snippet here, we see an operation that makes a call over HTTP to an external service. This is real code from a past code base I worked on. And it wants to retry if there's network or HTTP related errors. Interestingly, this particular call was part of a web crawler that was making calls to hundreds of thousands of servers out on the internet. And let me tell you, there's some wacky servers out there, especially if you're not controlling the list. And anyways, through trial and error, we discovered that we kept discovering more and more errors than we thought were enumerated in this rescue statement here. Unfortunately, the company folded before we were able to finish work on this component, but we had logs at that time, and there were 3 other error conditions that this clause was throwing and wasn't rescuing on, and in fact wasn't retrying on. that we did want to retry on. One of them was related to a corruption of TLS connections. There was another one related to TCP errors that weren't being caught. And anyways, long story short, I found the Ruby exception taxonomy model to be entirely awful. You had to go into the linked C libraries to figure out what could possibly be thrown in order to catch it. And there weren't many good generalized exception types to catch those very specific errors that were called out in C. And I found some languages are definitely worse at this than others, especially ones that have a thin runtime that do most of their work in a whole bunch of C libraries. In particular, I'm looking at you, PHP. Anyways, the point I'm here, the bigger point I'm trying to make here is that assessing what exceptions fall through the cracks of your catch statements is actually a useful tool for understanding what could go wrong in your application. In particular, when you don't have the checked exception model. And even when you do, if there's a concept of unchecked exceptions in any form in the language, you want to go investigate what could go wrong in what you're calling. I know this is pretty basic, but it's leading up to some of the other points. So moving on here. So one of Joyent's great contributions to Node, in my opinion, is the VER module, which brings the concept of chained exceptions to the language and runtime that doesn't contain it natively. I found when maintaining a long-running application that I get error reports for users, and I don't always, or many times, I don't have enough information to properly diagnose the cause of the issue without that information being embedded in the exception. I know we do a pretty good job mitigating this with core dumps, and I'll talk about that later, but let's suspend disbelief here for a moment and, or suspend belief, and imagine we didn't have that tool. So one of the helpful patterns I found to analyze the frequent sources of error conditions is that are typically clustered around I/O or external APIs as places where I want to improve, is by annotating exception with the relevant state at the time of the exception. And it's a very useful tool for doing this is the chaining pattern. To wrap exceptions with a more generalized exception type that contains useful information regarding the state of the system at that time. I think Joyent, we totally get this. I mean, I assume everyone has read our error guide for Node, for error handling of Node in production. I mean, that is, regardless of what language you're programming in, I think you should read that blog post. Actually, it looks like it's not even a blog post anymore. It's a first-class part of our site. Interestingly, I was looking through Rust, and chained exceptions aren't a first-class citizen of Rust. It is a an add-on like Node VER. So another pattern I've stumbled upon over the years, which I've only seen in one place, and that is the pattern of a contexted exception. I first discovered this in, and the only place I've seen it is in the Java Apache Commons library, although I do have an inkling that I've seen this elsewhere, because I've worked with a lot of languages. I just can't point to it. It's a simple pattern, and it essentially extends an exception type and embeds an associative array. This provides a standardized way to format all of the state that you might associate with an exception. In particular, I find this pattern encourages developers to include more state in their exceptions by reducing the labor involved in creating formatted exception messages. so you don't have to format a bunch of stuff in and think about how it works in the sentence. You can just write a sentence stating the generalized error message and then have all the state embedded in a key value uh, array, associative array. Okay, I'm the question I'm a little lost on. Maybe somebody could pipe up and ask directly.
Are you talking about the question in MIB?
Yeah.
Sorry, I was just pointing out that Node VError also has allows you to put an associative array in there, and they were
That's
talking
awesome.
about that, but I don't think there was a specific question.
Oh, okay. Okay, wonderful. I did not know that. That is wonderful. Okay, so like I said, I'm probably preaching to the choir here about this one. But anyways, so what's nice about this is you don't have to worry about formatting your exception. Also, if you've ever had to write a system where you have to localize error messages, this is a godsend. Because having to change all those format statements per language is really, really frustrating. Okay. Anyway, so what does this look like in action? Here's an example of a stack trace that was part of an error report given to us by a customer. Here you'll see that the state relevant to the specific error case was embedded into the actual exception. This meant that in the very first email that was sent to us, we had sufficient information to diagnose and fix the issue. And in particular, what this meant is we didn't need to go back to the customer to say, hey, go change your debugging logging level, or go collect more logs for us to have enough information to act upon the issue you're reporting. All of the relevant state needed for us to solve this issue was embedded in this. And I don't want to say that that can happen all of the time, because obviously many times, you need more information. But in this particular case, because of the way we had structured the state in exceptions, it was good enough. And I think you can aim to that to catch a number of those type of cases. So let's say you do have a case where you just can't get everything into the exception message or context. And in particular, you may have different threads, or you might have different operations in flight in a model that just doesn't work well to have all that state flow into your exception message, just because of different application architecture issues. So anyways, if you do have multiple operations in flight and there's no good way to tie all that state together, another useful pattern is MDC, multiple diagnostic context. I first encountered this pattern in Perl in the 2000s. I haven't been able to track down the precise Perl module it came from. I see it's in log4Perl, but I remember this in another more obscure Perl module before then. And that leads me to believe it's an old pattern, but unfortunately the sheer amount of references to Java in Google just overwhelms any pointers to anything I can find in older platforms. So I haven't been able to track down its history. Anyways, so with MDC, you can tie state that is relevant to multiple logging lines together and relate it to your exception messages. In particular, this is useful for doing something like tracking a request through a system or through multiple systems using a request ID. There is a big drawback with the typical MDC model, in that it tends not to work for programs with multiple threads in a non-blocking I/O model, because their work is switching between threads, and then MDC state is stored per thread. That's in a typical implementation. Additionally, there's something called NDC, Nested Diagnostic Context, that works in the form of a stack. It provides similar functionality, but it's a bit beyond the scope of the talk that I want to go into. Another thing that I've got to hide that toolbar. Another thing that has helped me in the past was being able to correlate such request identifiers in with requests out to a data store. So extending upon that notion of tracking requests or system, one useful pattern is to pass those identifiers into the data store when you're querying. Typically, this can be done as a form of a comment on the query. And interestingly, most data stores, relational or otherwise, they don't strip comments. And they'll actually present the comment alongside the query in logs. And even with tools that do introspection or some sort of, some sort of debugging analysis on the running queries. I know that Postgres in particular is good about preserving the comments. And this can be really useful for tracking down where in a system that a query is being executed from and what particular request is associated with that query. And you can do it purely from within the data store tier, which I found this particular pattern has saved me a few times over the years. One of the patterns that we have is, one of the patterns that we use to have uncaught exceptions in our node process to trigger a core dump and shut down the node process and then have Thoth capture the core for future analysis is us taking core dumps. And there's that sidebar again, sorry. And I found this has been an amazing pattern to see operationalized, and Joyent is the only company where I've actually seen this being done consistently. And I think it's excellent. But one of the things I wonder about is, like, there are cases where many companies and environments you can't execute on using the core dump operation as well. And I want to ask a question like, how would we envision using this pattern with a language and runtime that supports multiple threads? Would we shut down all the threads in a multi-threaded process in order to produce a core? Or, would the said language or runtime be able to produce a core without stopping the process and also be able to do it such that it doesn't impact performance? So, is there a way to do this with Rust, for example? I don't know. So, I know in some languages this is a really hard thing to pull off with multi-threaded processes. So you see a higher reliance on exception messages capturing all of the relevant state before a crash. Regardless of your ability to be able to pull off a dump and operationalize it properly, I do think you still end up having the problem where the number of dumps add up and you need a human to go inspect them to see what went wrong. Thanks, Brian. I was also conflating core and heap dump. So you have things like the JVM does a heap dump to provide a similar level of functionality to the user to be able to inspect the state. Yep, they are a kludge. Okay, so, but the larger point I'm trying to make here is that you do end up building up in sheer number of cores, and you want to start to draw inferences from multiple cores that have piled up. And if you can start to aggregate these in some way and be able to operationalize data mining upon them, I think that'd be a huge operational benefit. But I don't think having an ability to operationalize core dumps is a good argument for not building exceptions with actionable state or implementing good tracing practices. I think both processes are actually mutually beneficial. I'm not really making a straw man argument. I'm just saying that they are orthogonal issues to each other. Lastly, once you have your exceptions in an actionable state, the next logical step is to have exceptions stored in such a way that you can take action based on them in a deliberate way based on data. One of the things my experience has taught me is that like a good UI for visualizing the frequency, type, and severity of exceptions coming out of a system is a useful early warning sign for more serious issues. Of course, you can set up a system that sends out emails or does log aggregation of exceptions, but it doesn't give you a good way to pivot on the data, nor does it give you like a proper structured view of the most recent exceptions. And I think you want a tool that allows you to browse through the most common and recent exceptions in a system while having a cup of coffee. Like in many shops I've worked in, it's often a common ritual for engineers to come in the morning and go through the exception report list. And in particular, it helps you find out the weird outliers. One of the tools I've used that I've had a lot of success with in the past, is Honey Badger. And when you look at Honey Badger, you can see that you can sort by the most recent exception or overall count. We can also filter based on environment type and do things like use tags to indicate regions and filter by tags in a region. So, for example, if I take one of these exceptions and you dive into the details, you can see there's a considerable amount of state captured with each exception. In like we capture a number of things about the state here, fairly minor. I mean, it's nothing compared to say a core dump, but what's useful is the tool will allow us to generalize multiple exceptions, even though the particulars of its contexted state differ. So that we can have a view about the frequency of that particular type of exception as I go back to this view. So lastly, really, I don't see this approach as replacing the process of capturing core heap dumps, but as rather a complementary approach. In fact, I think you could probably unify a tool like this to basically point to the path of your captured dump when you do report out to the exception reporting service. And it might be a really nice tool then to have a link to multiple core dumps for multiple exceptions that it has done a best guess are all have the same root cause. And it would provide a useful jumping off place for that exploration. Lastly, I want to address any questions at this point. I know I've covered a lot of things that we've done deeply. This talk was really just intended as a bit of a reminder that we're going to have to think deeply about these problems in Rust going forward. So let me pause. Any questions or discussion? Okay. Lastly, I would like to remind everyone to sign up to do a JTD. I think they're an important part of our culture, and they really aid in everyone's learning. I went and jumped into this one, and it's obvious I don't have a deep knowledge of all of the tooling that we have built, and even some of the features of even the tools I mentioned, right? I encourage everyone to jump in, even if they don't have complete confidence that they can speak with absolute authority about everything, and not be afraid of what they don't know. So with that, unless we've got any questions or discussion anyone wants to bring up, I will end the session. Thank you, everyone.